In this video, I'm going to introduce the arithmetic and logical operations of the y86. We'll talk about all the various instructions. And when we talk about arithmetic and logicals, we talk about them as ALU operations. All the ALU operations have the same format. They're 2-byte instructions, where the first byte gives you both the opcode of 6 and a function code telling you which arithmetic or logical instruction you want to execute. So as shown on the slide, if you're doing an AND, then the function will be 0, subtract, it'll be 1, and it'll be 2, XOR, it'll be 3. Now, you're also getting 2 registers. You might say, but wait a minute, if I have an operation like AND, I should have 3 operands. There should be something plus something else equals something else. And you would be correct. However, on y86, one of the operands is also the destination of the operation. So if you look at the expression at the top of the slide, all the arithmetic and logical operations are of the form, the destination is going to go into the register referred to by register B, and it's going to be the result of applying the operation to registers A and registers B. What's particularly noteworthy is the order of the registers. For add, and XOR, it doesn't matter. But for sub, you really want to know which direction the subtraction goes. So the standard format is that RB is going to get the result of RB op RA. So if RB were 10 and RA were 1, after a subtraction, RB would contain 9. Because these are 2-byte instructions, the memory representation is easy to just read out of the byte pattern. Now, here's the big surprise. On the y86, we're going to give you some bonus operations. In addition to the 4 operations on the previous slide, we also support multiplication, division, and modulo. Multiplication, like AND, add, and XOR, the order of the operands doesn't matter. However, divq and modq, it's important to remember that the order of operations is that the result goes in RB, and it's RB div RA or RB mod RA. You may recall that the y86 processor has some condition codes, and arithmetic and logical operations is where the condition codes come in. So depending on what the result of the previous operation is, or of the previous ALU operation, the condition codes will be set such that if the previous operation returned a 0, then the ZF flag will be set. If the previous operation sets the sign bit, that is the high order bit in the word or in the quad word, then the sign bit will be set. And the overflow bit gets set if in fact the operation, when applied to the 2 operands, has a bit that overflows from one of the ends. We'll actually go through some examples and show you how the condition codes get set depending on different values in the registers. So here's a big, ugly example of some code whose sole purpose in life is to demonstrate how the condition codes get set. So what we'll do is we'll load it in the simulator, and I'll walk you through the different operations and show you how you can use the simulator to verify your understanding of how the condition codes work. So where we left off is that we had FFFFFE in a register, and I told you that was equal to -2, and we were going to add it to itself. Now, you and I both know that if you took -2 plus -2, you're going to get -4, and you might think that, well, that should clearly set the sign bit because it's negative, but it probably shouldn't generate an overflow, should it? And I'm going to show you why it actually will. Because what we have is we have 2 numbers like this that we're going to add together. The question is, when we add E and E together, what do we get? Well, you should scratch your head for a minute and say, well, 14 plus 14 is 28. When you represent 28 in base 16, that's going to be equal to a 1 for 16 plus a value of 12, which is going to be C. So what that means is that you get a C and you carry the 1. Now, all these are filled with F's. So when you take F plus F, that's 30 plus 1 is 31. You're going to generate another F here and another carry. And so what's going to happen is you're going to generate a stream of F's until you get to the end, and then notice that we generated a carry of 1. So when we add -2 and -2, we get the correct answer, and that really is equal to -4, but it also is going to generate that carry out to the left-hand side. At least that's what we think it should do. Now we can go back to the simulator and check and see if that's actually what it does do.